So looking at visual pathways, let's talk about some of the general anatomy. We'll get a little bit more into some microanatomy because the anatomy definitely feeds into how things do and don't work. So when we look at the eye is obviously the receptor portion of vision. And we have our retina, and this is where we have, like, we had our mechanical receptors for um for the different organs in the skin and things like that. But the eye serves as the receptors, specifically the photoreceptors, and these all live in the retina. Now, on the back of the retina, there is the functional unit, and then there's the non-functional retina. So the non-sensory portion has nothing. It's really just a double layer of cells, so nothing we were too worried about. And it kind of lives up here right behind the eyeball. The reason we don't want to have receptors there is because if light bounces off the back of the eye and we catch it in the front of the eye, you will get double vision. So we actually need this to not have any receptor cells there so we don't get double vision. Thank you all for helping her find those the PDFs links in the chat. Appreciate it. And then we have the sensory retina. And the sensory retina starts at something we call the ora serrata. This is where it starts, and it kind of is about 3/4 of the retina all the way around, all of it then ending and going here into the middle of the optic disc. So this is all of our sensory retina that just came up in purple. And that is going to be the part. Now we're going to zoom in. See that red box coming in there? That's where we're about to zoom in. So we're going to really dive in to the sensory retina. And the sensory retina, whoo, buddy, y'all, it is got a ton of layers. And we start up here with this nerve fiber layer. The nerve fiber layer is the layer that is closest to the inside of the eye. The pigment layer is on the outside. So this nerve fiber layer is the closest to the inside of the eye. And so light is going to come through first through this nerve fiber layer and then has to go through all these layers before it gets way down here. And we're going to break down and talk about each of these layers individually. Some layers are more important than others, all right? Here are these layers in histopathology. So even when you look at these, the reason we have all these layers is because histologically we can see different layers as they come into play. And so what are some of these layers? So we're going to start here at the bottom. So we'll start here with our pigment epithelium, and we're going to work from the outside inwards towards the eye. So the retinal pigment epithelium is that most outer layer of the retina. It actually contains melanin granules, and this helps to prevent diffusion of light. All right. And so we have it so that it can absorb some of the light. So if we get extra light coming in, we want to get rid of it. And so the black will help to absorb some of that through the melanin, and that can help do it. Now, we all know that some species of animals have the ability to have better night vision. That's because they have this tapetum lucidum. The tapetum lucidum reflects light and allows it to kind of expand, and so it increases the light available to the sensory retina when the world is dark outside. The other big thing that the retinal pigment epithelium does is it is responsible, other than providing retinal pigment, it is where these cells, these rods and cones, get nutrients and oxygen. That is why when we have retinal detachment and we detach from this epithelial layer, we can sometimes not get return of function, is because they lose their connection to their nutrients and their oxygen. And so this is some histopathology of it. If we look at part B here, what we're missing is that melanin within that layer right there. And so this is how we know that this is the tapetum lucidum, because we have an epithelial layer that has no pigment. And so that's how we know we're in it. In most eyes, we're going to have this pigmented epithelial layer. And again, this is what is absorbing extra light so that it just doesn't bounce around the eyeball and then create confusion or overstimulate our rods and cones. So then we have what is probably the most important layer. All right. This is the photoreceptor cells. And this actually makes up our photoreceptor layer and our outer nuclear layer. So these rods and cones make up two layers of the retina. So the photoreceptors are going to be this outer segment. And this outer segment is made up of either rods or cones. Rods are sensitive to light, cones equal color. Rods light, cones color. And so rods are what allow us to see. So if you got to get up in the morning and you got to go to the restroom, what little light is out there is being picked up by your rods. That's why if you were ever like in these low light areas, you might actually pick up and think that you're seeing in black and white. Like you might almost get kind of a gray color. And so if you're ever like out walking on the road and you see a stop sign, you're like, that stop sign looks more gray than it does red. Well, that's because you don't have enough light for color to be seen. And so you're kind of seeing a black and white and you're really seeing rods. Now, in addition to having tapetum lucidums, animals also have more rods than they do cones. Dogs, for example. So that also feeds into better night vision. So even without that tapetum lucidum, they have more sensitivity to lower light levels. And then rhodopsin is the chemical that kind of gets excited, gets stimulated due to light. So rhodopsin, rods, light. When we deal with cones, cones respond to specific light frequencies. Remember that when we have color, color is a response to light frequency and how light bounces off of whatever pigments are in there. And so we can stimulate the idiopsin, aka the photoopsins, that are within these cones. And if we get frequencies that are consistent with red or consistent with purple, etc., that can stimulate those cones, get the idiopsin fired up, and then that can convert to an electrical signal. The outer segments of photoreceptors, so that let me rephrase that. The photoreceptors are in the outer segment, and that is going to be right next to our pigment epithelium, because remember, we're going to feed the nutrients and oxygen directly to them. All right. And again, nothing really else new in here, but this is going to be the layer. So we're going to kind of either absorb light or bounce light off of the retina, and then we're going to collect light here. So if we had to have like, what is the most functional unit of the retina, it's going to be this photoreceptor layer, specifically the outer segment, because this is where light's taken in. And again, we kind of dive back into rods, rhodopsin, cones, idiodopsin, in terms of what is the portion of it that's getting excited. So when we talk about seeing in color, we know that different animals see in different color variations. We have three different opsins. Dogs are dichromatic. They only have two different opsins, and that gives them a violet sensitivity and a yellow-green different sensitivity. Birds and fish are tetrachromatic. So y'all, there are colors that we cannot appreciate that they can, which I think is wonderful. And so you can kind of see the differences. We have this little girl here. You can see what we view her as, and then how a dog would view this little girl. Right? You can see that they're definitely more purple-yellow. And then if we look down here, we can kind of see what a cat, again, also a little bit more in that purple-yellow, but just not as vibrant as the world goes. And then if you have no color and you just kind of live in a black and white world, you're going to see shades of gray. All right. When we talk about dog color, they struggle with some differentiation from their grays and their blues and things like that. Interestingly enough, how distributed these rods and cones are also plays into how much the sharpness and the color contrast and all that plays a role. All right. And so where we have the sharpest differentiation of color, ours is all cones. All right. We have a lot more cones than dogs do per retinal square inch, if you will. Dogs only have 5% of cones. So what color they do have, they're not contributing a lot of life or a lot of effort to color, right? Does a dog care what color the walls are of their doghouse? Heck no, y'all. What do they care about more? Is their ancestors, the wolves, really being able to see prey in low light areas. So for them, rods are more important. Same thing with cats. They want that visual acuity in low light. So it makes more sense for them to have more rods. So then we're going to have our outer nuclear layer. This literally just contains the rods and cones nucleus. All right. The outer plexiform layer, which is here highlighted in blue, this is really just where we have synapses coming through. So we're going to synapse the dendrites of, the axons of our photoreceptor cells with the dendrites of our other layers, specifically the horizontal and bipolar cells. So the outer plexiform layer is just where cells connect and communicate. So what cells are in this inner nuclear layer? Remember that outer nuclear layer was the nuclei of our rods and cones. This inner nuclear layer is our bipolar cells. These guys are basically converging on multiple ganglia, and they are connecting ganglion cells, which really are functional units of the optic nerve, and they are connecting the rods and cones. So think of the bipolar cells as middle management. They are connecting the rods and cones to the cells that will soon form the optic nerve. Horizontal cells run horizontally, i.e., they connect horizontally. And so what they do is they make horizontal connections or lateral connections of multiple cones and rods. And what this does is it helps us turn on or turn off different cones and rods to help with sharpening the edge and sharpening contrast and things like that. And then amacrine cells are going to actually serve a similar purpose in that they connect multiple ganglion cells. And they're going to help us modify the bipolar cell output. So what does that mean in quick, dirty terms? Bipolar cells connect rods and cones to ganglion cells, i.e., the neurons that form the optic nerve. The horizontal cells connect and communicate rods and cones to each other. Amacrine cells connect and help ganglion cells communicate to each other. So that's kind of the quick and dirty of those. Then we're going to have another inner plexiform layer. This is where bipolar cells and amacrine cells and all of those are going to have their connections to the ganglion cells. So these ganglion cells are the innermost cell bodies. These are the neurons that are going to be the final neuron that fire before we send all of these axons into the optic nerve. And then interestingly enough, our nerve fiber layer contains all the axons in the ganglion cells. And what they're going to do is they're going to leave, they're going to travel inward toward the optic nerve, and they're all going to converge on that optic nerve so they can go inward. It is not until we get to the inward portion that these cells start being myelinated. And this hopefully makes sense. If I myelinate all of these axons, and myelination, remember, is going to be that fatty coverage of the axons. If we have that fatty wrapping, now they're thicker. Now it's harder for light to get through and bounce back. All right. And so we're not going to myelinate them until we get to the optic nerve, which is actually a visual dead spot. So we can start myelinating it there and then increase how quickly that we can get this signal to travel. Now, here's a dirty little secret for you. The optic nerve is not a real nerve, all right? And this is by definition of how it's constructed. So even though we call it the optic nerve, it is technically an extension of the central nervous system. How do we know that? It's because its myelination comes from a cell called the oligodendroglia. And this oligodendroglia helps provide myelination to all central nervous structures. This is in comparison to the nerve. The nerve gets its myelination from what's called a Schwann cell. And so we have the Schwann cell for the peripheral and the oligodendrocyte, which is going to be a central nervous system. And so we can say that, whoa, hey, if it's an oligodendrocyte, that means it's part of the CNS, which means the optic nerve is not a real nerve. It is an extension of the central nervous system, which is, y'all, this is probably the sexiest thing about neurology. You can look in an animal's eye and you can see its central nervous system. There is no other place on the body that you can look into or at an animal and see the central nervous system. So like, hot damn. All right. So keep that in mind that this is the only part of the central nervous system we can see. It's technically not a nerve, but we're going to call it the optic nerve. All right. And this is the only part where it's going to be myelinated is there at that disc. All right. And this is the optic disc. So we're going to dive deeper into that optic disc, which remember is where all of these axons of the retina are going to converge and start to myelinate. Now, we have a couple other cells that are hanging out here in the retina. All right. They're going to be neuroglia. They're going to provide support and structure to it. So just know that they kind of exist. And radioglial cells, i.e. Mueller cells, are all about extra structural support. Now, I want to take a moment and I want to slow it down, okay? Because that's a lot of information in a very short amount of time. So what is happening so far? So light is coming in, and we're going to take it into our eyes. We're going to go and we're going to bounce it in to our eye. All right, so I'm blowing up the retina. Boop. Light's going to come in, go all the way through the eye, and then it's going to go and it's going to hit the retina. Light has to pass through all of these layers because remember, this pigmented retinal layer is on the outside. It's closest to the outside of the eye. The ganglion cells are closest to the inside, meaning our light has to travel through the retina and get to that very basal surface where extra light's going to get absorbed by the pigmented cells, all that melanin, and then the rods and cones are going to get stimulated by the light that comes in. Now, you might be asking, who done created this, right? Because why not put the more sensitive ones out here? I'm glad you asked. If I put the rods and cones out here where the ganglion cells are, closer to the center of the eye, where we keep that vitreous humor, what happens is a little bit of light will go back and not all the light will be absorbed by the pigmented epithelial layer. Some of it's going to bounce off. Well, when it bounces off, what's going to happen is you're going to get light causing stimulation as it comes in, and then light getting stimulation as it comes back. And so you're going to get, again, that double vision and a double dose of light. So it's not actually going to be representative of what you're seeing. So the closer we can put it to the wall of the eye, the less likely we're going to get crosstalk or extra stimulation from light. So light comes in, passes through these layers, gets our rods and cones all sorts of stimulated, depending on if it's degree of light or if it's color waves, right? Depends on what it is. That's going to excite the opsins. The opsins then are going to help create and stimulate that light into an electrical signal. That signal then is going to be sent from the rods and cones to the bipolar cells, from the bipolar cells then to the ganglion cells. The ganglion cells then have axons that travel across and transverse the retina, that then all come together at the level of the optic disc. And the optic disc then is where we're going to start forming our optic nerve that is then going to go into the brain. Any questions on how the retina works? A very thin structure Yet one so very, very, very important. Any questions? Beautiful. Sweet. Okay, so we will keep on keeping. So now we're going to take that retina and we're going to bring the light in and we're going to bring that signal from the retina into the brain so that we can process it. Couple little anatomy things to throw back at you. The optic nerve, i.e., not a real nerve, travels via the skull through the optic canal, right? So we're going to send cranial nerve 2 through the optic canal. When we get into the brain cavity, the right and left optic nerves are going to come together in front of the pituitary, i.e., the hypophysis, to form the optic chiasm. So where left and right nerve come together, that's going to be our optic chiasm. All right. Now, I want to point this out to you, and we'll reiterate this as we get into more clinical things in future years. When you lose vision due to neurological conditions, it is really, really hard to get vision back from neurological conditions. Why? Because look how freaking complicated this stuff is, right? Like, that was just the receptor. We had 6 layers of just receptor, right? Well, now we're going to have pathways, and now we're going to have neurons, and throughout growth in life, your cortex has been mapping out what each little rod and cone does. Like, y'all, complicated. So the sooner you can get in and start doing different things and start your therapies, the more likely you can. But I always tell owners is like once vision is lost due to neurological symptoms, it can be really, really hard to regain it. So I just kind of start that from the process of early on saying, hey, we're going to do our best, but just be prepared. All right. If I use the term decussate, remember that means it's going to cross, often crossing the body. Contralateral means the opposite side. Ipsilateral, same side. Afferent means we're sending sensory information to the central nervous system. It is ascending to the brain via the afferent or ascending sensory tracts. Efferent exits the brain and is motor information going down to the body. All right, this is where it gets really wild. So we have different types of zones of visual ability to see, okay? You have your binocular zone, which is where your left eye and right eye overlap. And then we have a monocular zone, sorry, words, which just means only one eye can see it. Now, it's super, super easy to find this. So what I want you to do is kind of away from your computer so you don't slap it. What you're going to do is you're going to close one eye, whichever eye you don't like, close that one first. And then you're going to bring your hand up in front of you and you're going to take it out until you can just barely see it in your periphery. Keep looking at your computer, keep looking straight. And once you no longer see your hand without looking at it, like I just want you to look straight and see it in your periphery, stop. Okay? And so that is the extent of where your vision is for one eye. Okay? Now, what I want you to do now is close your other eye and open it. Now, bring that hand that's up back center. And once you get there, stop. So now you're using the eye opposite to the hand you're using. So I'm using my right hand, but my left eye is open. And I'm bringing my hand up to where I can just see it. So I'm moving it from the extent of my periphery vision up to where I just barely can see it in my left eye. The space that your hand just moved is the monocular zone of your right eye. Now, if you do the same with your left hand, and now open your right eye, and we're going to bring that left hand central. until I can just barely see it in the middle portion of my eye. So now what you should have is two hands kind of almost like straightforward like this. This is your binocular zone. This is the zone that you can see out of both eyes. Everything lateral to it is your monocular zone. And then once you've maximized how far you can see with your hands, that is your limit of your peripheral vision. All right. So kind of a nice little exercise that you can do with that. Why does that matter? All right. Because when we talk about left eye versus right eye, what we're actually talking about in veterinary medicine a lot of the times, especially with like menace response, is going to be visual fields. And when we talk visual fields, right, left visual field, right visual field, it is the visual fields that are what's being interpreted by the brains. So the right visual field is being interpreted by my left brain and vice versa. Now, what we have in dogs is that the nasal 75% of the retina, so look here at B with me, the nasal 75% of the retina is going to send information to the contralateral visual cortex. So my right eye has a big role in my right visual field. But if we look over here on the left eye, you can see that the temporal portion, or the more lateral portion of my retina, has a 25% responsibility. So the left eye in dogs sees 25% of the visual field of the right eye. This decussation varies between species. Some species, like you and I, are 50-50. Cats are 65, ungulates are 90 to 80%, fish are 100%, and birds vary. All right. But again, remember that the visual field is interpreted by the opposite side of the brain. It's a great kind of simplistic takeaway. So let's view this in a different light. See, light, vision, cool. All right, so look at my blue circle. My blue circle is, if this is a dog, 75% of this is responsible for being seen by my nasal retina of the right eye, i.e. the medial retina of my right eye. So this is going to come in, and this light's going to go, and this is the majority of the fibers. This is 75% of fibers in the dog are going to come in, and they're going to cross at that optic chiasm. They cross at the optic chiasm, and then they're going to come in here, and they go boom to what we call the lateral geniculate nucleus, which lives in the diencephalon. They're going to travel up to the optic radiation and be controlled by the left cortex, specifically the occipital lobe. So then if we look, and Brandy, this is kind of, we're going to get to your question here. If we talk about now this left eye, the left eye is responsible for about a smaller function. And when we say 25%, let me clarify that 25% of both the retina and the fibers are going to be coming from the left eye in the dog. So about 25% of the retina is going to be dedicated to seeing the left visual field, because percentage of axons that leave the rods and cone is going to be equitable to the percentage of retina real estate that's going to be involved. All right. And so this left eye, the temporal retina of the left eye, about 25% of that retina is going to be focused on the right visual field, where my circle is, and the blue light coming from that circle. So as it comes in, it's going to down. 25% of the fibers from this retina are going to come down and not decussate. They're going to stay ipsilateral, stay on the same side. And those are going to go back and be programmed to that left visual cortex. So our temporal retinas, the information that comes from those, does not cross, does not decussate. And that's where the percentages come from. The percentages are the percentage of axons that decussate at the level of the optic chiasm. which in a dog equates to about 25% of the retinal real estate being involved in this visual field. And again, that's highly variable between species. So what's the big takeaway? Right brain interprets left visual field. Both eyes see part of the left visual field. And again, you have your binocular zones and then you have your uniocular zones. So, or monocular zones, depending on which
So
literature.
I have a question. So
But
are you saying that um like how you said the left eye will see what 25% of the right side of the body is what you're saying?
so it's less that it's seeing 25% of what's around here, but it's that 25% of the retina information is dedicated to the visual field. And so it's hard to say like 25% per se, but it's more of 25% of the axons that leave are applied. And so you can flip that. And so if the left eye has sends 25% of its axons are responsible for the right visual field, the right eye has 25% that is doing the left visual field.
And then you would say the other 75% is going to the opposite side of the body.
Yep. Yep. So
Okay.
yeah, so it's very the best way to say it is that 75% of the information is crossing over.
Okay, thank you.
Yep. And so the nasal retina controls the majority. And again, this is all because we're not dealing with a flat surface. We're dealing with a circle, right? Or a sphere. And because we're dealing with a sphere, we're taking this flat surface and we're doing this, right? And so just the way that light works and circles work, spheres, sorry, that this side is going to see over here, this side's going to see over here. So then we can just mediate who's the primary based on percentages, if that makes sense. So the more that we care about what we see out of here, the less we see over here. But again, you can kind of see if you look at this one, you can see the percentages different. So we can see that this all varies between different species, where their eyes are set, how they're set, all of those kind of things. In general, prey species have eyes that live more laterally placed, right? They need a wider field of view because they need to see the tiger coming up from behind them. Predator species tend to have more forward-facing eyes. Smaller field of view, but better binocular vision equals better depth perception equals better pouncing power. So the more depth, the easier it is to pounce on your prey. There's a lot of P's in that. So let's revisit and talk about the visual pathway. So this is how we see. This has nothing to do with our pupils. This only has to do with what we see. So light comes in, hits the retina. From the retina, we're going to stimulate the entire globe, and we're going to send that signal up the optic nerve. At the level of the optic chiasm, two things will happen. The 75% of our axons from the nasal surface of the retina will decussate at the optic chiasm. All right. 25% of the axons in a dog will stay ipsilateral. Both of those axons now will travel to the respective lateral geniculate nucleus that they're supposed to go to. So the majority of fibers from our left eye here are going to the right geniculate nucleus. 25% are staying on the left side and going to the left lateral geniculate nucleus. We will have a couple axons that tiff off and go do some other things, but we're not going to worry about those right this second. This is our visual pathway. From there, we're going to have axons that leave the lateral geniculate nucleus, travel up the optic radiation, and go to the visual cortex on the contralateral side for that field of view, i.e., visual field. So that is how we see. Now, we did take a few of our axons and we're going to put them into the rostral colliculus. The rostral colliculus is in the midbrain and is what's responsible for visual reflexes to retinal activity, right? If you are walking down the street and someone shines a flashlight on you, what are you doing? Well, you're going to respond. Well, they shouldn't say anything because then that's a whole different part of the brain. If they only shine their light on you and you go, huh, all right, when you see that light and you turn, that is your rostral colliculus getting activated, getting excited because it's responding to light. So it is reflexive movements responding to light is the role of the rostral colliculus. Rostral colliculus is involuntary reflexive movements in response to light. It's also why you're like, stop. It's involved in the dazzle. Like, stop, get that light off. Right. So be able to kind of describe or label this pathway. How does left or right visual cortex gets its information, and how do visual fields differ? Now, in humans, this is even more complicated because we can break vision down into quadrants of each eye. We're not going to get into that in veterinary species because it doesn't matter, because we can't ask them where they can see the thing moving. Like when you're doing a driver's test, you're going to get up here on the right, bottom left. You're going to have all 4 quadrants of each eye tested. It doesn't matter in dog because they can't talk. Now, this is a great example. So you may hear that the dog is standing here at the bottom of the screen eating. And he's like, I'm going to only eat on the right side. Uh-oh. What this means is he's only aware of the right side of his world. Okay? So even though there is food there on the left, he doesn't see it. So this is a great indication that he's aware of his right visual field. That means his left cortex is working. But if he can't see this food, all right, the food on the left side of the bowl, that means his right cortex is probably not interpreting that there's food in the bowl. So what's happening is his eyes are like, yep, information coming in. I'm seeing the light, but the right cortex is not aware that that is food. It can't distinguish that as food, so he's not going to eat it. He doesn't know what that is because he's confused, because he probably has an issue or a lesion with his right occipital cortex, so he can't interpret. He can't apply meaning to anything he sees in his left visual field, if that makes sense. So food is not food. For all he knows, foods is rocks, because his brain can't use that information and can't make sense of it. We already talked about the rostral colliculus. I more care that you just aware that the rostral colliculus equals reflexes for vision. That's kind of the quick and dirty of it. And I think this is just more reiteration of that. So what's nice is so far, the only difference for these reflexive pathways is everything's the same up until we head to the lateral geniculate. Instead, we go to the rostral colliculus. That's the only difference. And again, don't get too caught up in the pathway for the rostral colliculus. I just more want you to know what the rostral colliculus does. All right. And the rostral colliculus, just for orientation, is this RC right here in the middle of the diencephalon. So that's where those fibers are going. This is the dazzle reflex test. So we're going to shine a light in the dog's eye. They're going to blink in response to light. This is a subcortical reflex. They're going to close their eye because they're like, it's too bright. And so if they dazzle, that is a great way to test if that rostral colliculus is working. Also a great way to tell, is light getting in through the optic nerve of the chiasm, and is 7 working? Because you need 7 to blink. So sympathetic innervation, we're going to just real quickly go by because I know you guys get it in other classes. Just remember that sympathetic innervation can technically start in the hypothalamus. It goes from the hypothalamus down the neck and kind of comes out around C8 to T3. When it comes out at C8 to T3, then it has to travel through these guys and then up to this cranial cervical ganglion that kind of lives at the base of the skull, and then up to the eye. So a lesion anywhere, especially C8, T1, T2, even T3 spinal cord segments, can lead to Horner syndrome. Mediastinal masses can lead to Horner syndrome. Neck issues. So if we go in and we do a ventral slot and we are too rough on the sympathetic pathway as it travels up the neck, can lead to Horner's issues. So lots of areas that Horner's pathway can be damaged. If you want a more detailed version, this is it for you. All right. These are your 4 big loss of sympathetic input for Horner syndrome. This will be on your NAVLE, and then know what's different in horses. Horses, the meiosis might be more subtle. These, you can see the eyelashes having more ventral downward. In animals, horses will sweat with Horners. It's just a unique thing about them. Horses sweat with Horners. All right. So I wanted to make sure we got to visual reflexes. So visual reflexes and the pupillary light reflex, right? These are reflexive changes in response to light. What happens, though, is that this reflex is consensual, i.e., if I test this patient's left eye directly, I'm going to get a consensual response in that other eye. Okay? When one eye is illuminated, the other light does respond, and that is the indirect or consensual response. And so when we're testing PLR, we have to say which eye we're stimulating. So in this example, we're stimulating the dog's left eye, and we're getting a direct response in the left eye, and we're getting a consensual response or indirect response in the dog's right eye. So that's how we're going to use that terminology. PLR does not test vision. It only tests if the pathways are working. It is a light yes or no question. PLR tells you nothing about vision, i.e., an animal can be blind, cortically blind, meaning it cannot interpret the world. It is effectively and functionally blind, but still respond to light. So responding to light does not mean that you can see or understand what you're seeing. So the direct response, you're probably looking at this dog and being like, why is the direct response 100% constriction versus the consensual 50? The reason that this happens is that a large majority of optic tract fibers cross at the optic chiasm. And so the vast majority of those fibers are going to cross it once we stimulate the direct. Remember, we talked about in a dog, 75% of axons decussate. So 75% of the signal, 75% of the information is going to cross. Well, with the PRL pathway, it's going to cross again. And it's going to go back to that eye. And so the strongest signal is going to stimulate that direct eye because it crosses twice. 25% of the signal, right, is not going to decussate, but then it will decussate, and don't worry, we're going to go through this, and is going to go to the other eye. So the signal going to the other eye is just not as strong because of how dog eyes decussate. Now, we are 50-50, all right? Songbirds is 100%. So you get variations in this. So let's break this down a little bit. So let's focus on our direct pathway. We are going to stimulate this left eye. So we're going to shine light in. There it is. There it comes. There's the red eye. It's going to hit the retina. It's going to go through all of those layers that we talked about. We're going to stimulate the ganglion. It's going to travel via the optic nerves. And because this is the direct eye, the direct pathway, we're going to follow the majority of the fibers. We're going to follow in a dog the 75% of axons that cross at the optic chiasm. When they cross, this is where, so once we get to the chiasm, behind the chiasm is where vision and PLR pathways separate. Up till now, they're the same. But once you get to the chiasm, PLR pathways separate from the visual pathways. Vision went to the lateral geniculate nucleus. We're not going there. All right, we're going to another bus stop. We're going down to what's called the pretectal nucleus. So the pretectal nucleus is involved in the PLR pathway. And so what we've done is we've come in, the majority of our fibers crossed to the optic chiasm, went down to the pretectal nucleus. When we stimulate the pretectal nucleus, it's going to cross again. The majority of fibers are going to cross again. And these are going to cross the parasympathetic nucleus of cranial nerve 3. Woo! Cranial nerve 3 involves the ocular motor function of the iris. This parasympathetic nucleus pretty much all revolves around the iris. And so when we stimulate the parasympathetic nucleus of cranial nerve 3, that signal is now going to go up to our ciliary ganglion, which is going to directly control the parasympathetic supply to the iris, which means we're now going to get direct constriction of that eye. So that is the direct pathway. Light in, optic nerve, crosses at the chiasm, goes to the pretectal nucleus, crosses again to the parasympathetic nucleus, travels up cranial nerve 3 to the ciliary ganglion, and then causes parasympathetic supply and causes us to constrict the eye. All right. So this is the short version. If you're a reader and you like paragraphs, here's the long version. Let's talk about now what happens with the indirect light. So we're still going to stimulate the left eye in this scenario. So light comes in, follow the purple, optic nerve. But what happens? Oh, because the consensual or the indirect pathway is going to follow the minority of fibers, we don't decussate. When we don't decussate, we're still going to go to the pretectal nucleus, but the difference is we're now going to the ipsilateral pretectal nucleus. When we go from the pretectal to parasympathetic cranial nerve 3, we're going to cross over. We're still going to have the majority of axons between the pretectal and the parasympathetic. That's a separate axon, so we no longer have to worry about the 75%. So we're going to follow the majority of fibers that go from pretectal to parasympathetic nucleus of cranial nerve 3. That's going to go out that axon of parasympathetic nerve of cranial nerve 3 to our ciliary ganglion, and that will now lead to constriction of the indirect eye. So even though I didn't stimulate this eye, I still get constriction in response to the light in the left eye. If you're a reader, here's your paragraph form. Now, let's put these together, because in reality, these two occur together. So I'm going to shine light in this eye. Watch what happens. We got a red line and a purple line. Purple line coming down. Purple line does not decussate. Red line does. Both of them now go to their appropriate pretectal nucleus. They both cross. They both go to parasympathetic nerve, up cranial nerve 3, up to the ciliary ganglion, and they both lead to constriction. But look what happened. The direct, because it had more axons from the time that it left the retina and traveled through the optic chiasm, it had the majority, it had the stronger signal, so it has a stronger constriction. Parasympathetic only got 25% of the signal, and so its pathway was not as strong, and so we did not get as strong of a constriction in that indirect eye. If you like diagrams, graphs, this is one that comes out of Thompson, talks about the visual cortex. That's going to be a green pathway. This purple pathway is going to be the parasympathetic connection for the light reflex or the rostral colliculus. And then these red ones are going to be involved in your pupillary light. So lots of different things to consider, but a great, otherwise easy to describe. And then I just threw in here for you guys to kind of go through and look at some of these different pathways, Menace response and vision. But the big takeaway from Menace response is cranial nerve 2 to see, but cortex to think. All right. And so when you're testing Menace response, it is not a reflex. It is learned. You have to learn that the world is bad and evil, and that takes time. And so you will not have a Menace response in a patient that is under 12 weeks of age. It's a very complicated pathway. So in its simplest form, 2 to see, 7 to blink. If I'm testing the right visual pathway, like the right eye, I'm typically testing the Menace response of the left cortex. We'll talk about Menace response more as we get into more clinical examples, and especially as we go down the path. I know I'm 2 minutes over, but again, just remember, vision is probably the most complicated thing. It took me 4 years of vet school to understand vision. All right. It was one of the last things that really settled in. Spend time with it, take time with it, go step by step through the PowerPoint version, but then also look at that worksheet with the lesions, because understanding what goes wrong and what happens when things are broken can help inform the why and inform some of your understanding. That's why I like giving you those lesions as part of the basics version of understanding the anatomy, because if you can understand why it's broken, you will understand the normal anatomy. So for those that need to log off or anything else, please feel free. I'm happy to hang around and answer any questions, and I will keep this recording going. And then I'll find a way to link this recording for you guys as well, so that if you do have to hop off and want to hear some of the questions, you can come back and look at them. Otherwise, y'all, thank you for your attention. Woo! This is a dense day. I know it is. It's a dense day and 1 hour to talk about it. But we'll spend a little bit more time talking about it when we talk about the lesions. I believe next week, maybe in 2 weeks. Don't quote me. You're very welcome, y'all.
Thank
I had
you.
a quick,
Thank
I had a
you.
quick question.
Yeah.
Do we know what the reason for the decussation is? Like what?
Why? You might
Yeah.
have taken God himself.
Mm.
A lot of it, just think of it. Remember, our body, the left body, is in control of the right side, right? And so the eyes and visual pathways are going to follow the suit, right? Because if I'm controlling what happens over here, it makes a lot of sense to just have the body and the visual interpretation be controlled up here. Why isn't right, left? I don't know. I don't know where the evolutionary or structural benefits come through. I'm sure there's papers and people who have dived into this. I've not dived into the kind of the thoughts behind the evolutionary reasons for it. That being said, there's probably something that has to do with having to handle information coming from 2 eyes in one side, and that connection probably is stronger somehow. I mean, it's kind of a hard thing to think through, but I bet we could dive into the kind of why the evolutionary wise type thing, or why it was designed that way. But I don't have a great reason of why decussation versus the species that don't have decussation.
Okay. Yeah, I was just curious.
It's a great question.
I had a question about the Horner syndrome in horses.
Yeah.
For the sweating, is it only on the side with meiosis?
Yeah,
That
only on
sweats?
the affected side. So there we go. So this is the normal side of the horse. And so the sweating is occurring on the side with Horners.
Is that like just concentrated on the head, or does it go down the neck?
It'll go down the neck. It goes down the entire neck. Yep. And that's just because that there's innervation of those sweat glands, pretty much kind of from that head and neck region that comes from the Horner's pathway. And so when you lose that innervation, the sweat glands kind of go wild.
Okay, thank you.
Yeah, absolutely.
Thank you.
You're welcome.
Thank you.
You're very, very welcome.
I have a question.
Go for it, Jennifer.
When we were talking about the pathways, you said behind the chiasm, you said vision and something else separates.
Yep. So
Mhm.
what happens is one, like the visual pathway and the PLR pathway share the same, is all the same up until the optic chiasm.
Mhm.
Once we leave the optic chiasm, the tracks split. And so what you'll have is the visual pathway now will send signals up to the lateral geniculate and then go up towards the cortex. But the PLR pathway is going to stay down here in the diencephalon. And so up to the optic chiasm, we have the same thing. And so what you'll do is you'll hear people talk about, is this a pre-chiasmal lesion or a post-chiasmal lesion? And as you dive into some of those cases in that worksheet, you'll see that, oh, if the lesion is like of the optic nerve, both vision and PLR are affected. But if the lesion is behind the chiasm, then only one or the other is going to be affected.
Okay. Okay, thank you so much.
You're very welcome. Great question.